Okay, I started the streaming in YouTube.
Mhm.
Then I will, at the end, I will cut the beginning. It's
Mhm.
easy in YouTube to cut the beginning. So,
Mhm.
okay, I started the streaming in YouTube. Uh,
Mhm.
um, then I will, at the end, okay, YouTube has a little bit of delay with respect to Zoom, like 10 seconds. That
Mhm.
is nothing. Um, okay, and then come back here. Enrique is here. Enrique, do you want to say hi or something?
Hello,
Yeah,
can you hear
hello.
me?
Hello,
Yeah.
Enrique. We can see you, but well, we believe you are there. So I was introducing our group to Igor before starting. I believe that I contacted people in Salamanca too to attend the seminar, or at least watch the YouTube channel now or afterwards, because I know that Carlos Tejero and people from the group are also interested in this talk.
Mm.
So everybody's over there. More participants. Carlos Tejero came. Okay, good.
Ah,
So today is not only Madrid, it's also Salamanca team.
well, it would be great to be in Salamanca again.
Have you been?
Yes, so 20 years ago.
Oh, Carlos, say hi at least. So we can start and we don't feel so lonely here
Mm.
because of these online things have the problem of people watching it later and it's a little bit lonely.
Well, people do not know what to expect, but I will try a little bit to entertain you.
I'm sure. Alejandro Calleja is a PhD student, is also joining now. Okay, so I guess that there will be people joining during in a couple of minutes. But to not destroy your schedule,
No,
let's
it's a fine. So just let me know when I have to
okay.
start in an optimal way. Since I have not planned anything for today's afternoon. If you think people would come in the next 2 minutes, I can wait for 2 minutes.
Let's see. I mean, let's just start no further than 12:05, something like that. Okay. Okay, let's try. A ver, let's start, and if somebody comes in the during the talk, I will admit it and so on. So I will we try to share, and if it works, I mean, you try to share your screen if it works. It's working perfectly, so I don't have to make you host again. Okay, perfect. So it's a pleasure to introduce Igor Burban from University of Padeborn. Um, he's going to talk about algebraic geometry of the classical jump master equations. We are so pleased to have him here to explain a work that spans several years, as I understand. So thank you very much for giving us this seminar.
Thank you, Marina, for this very kind invitation to give online talk on a topic on which I indeed worked for many years. When we speak about in-vector equations, first of all, one has to say that there are many versions. There is a quantum in-vector equation, there is associative in-vector equation, also the theoretic in-vector equation, and today I'm going to talk about the classical one. And to begin with, I would like to take a simple finite-dimensional complexly algebra. And if you take G equal to SLN, so this is well enough for purposes of my talk. Now, the classical Yang-Baxter equation is a condition on a meromorphic function of one variable with values in the double tensor product of the Lie algebra with itself, satisfying this condition. The meaning of upper indices R1, 2, R2, 3, etc. will be explained immediately. Namely, for any pairs of indices, like 1, 3, I can first apply my function R, and then there are various ways to embed double tensor product into the triple tensor product. So I can do it for 1, 3, for 2, 3, 1, 2, and so on. In Lie algebra, I do not have 1, so that's why I need to take the universal enveloping algebra. And then in the triple tensor product, I take the commutators arising in the expression above. And it is one of the versions of the classical N-Baxter equation. So if we do not want to use the universal enveloping algebra, well, then we can convince ourselves that for simple tensors, we can perform all the operations needed to define the classical N-Baxter equation. Well, and see that indeed commuting to tensors for 1, 2, and 1, 3, we indeed get something in the triple tensor product. So it is a classical N-Baxter equation. And at this place, I have to say that it is a very important equation for many purposes. So mainly for the theory of classical integrable systems, maybe some of you have heard about Adler-Kosten-Syme schemes to generate integrable systems, but also other models in mathematical physics, are related to the classical N-Baxter equation, so solvable lattice models, some soliton equations, and there are some pure algebraic aspects related to that. And mainly, they all arise in the framework of quantum groups, but also Libye algebras and Lie-Poisson groups. Summing up, it's indeed a very important equation, but maybe you want to see some examples before I proceed more with a general theory. So the simplest simple Lie algebra we can imagine is SL2, and it has this distinguished basis. And the first solution of the classical N-Baxter equation ever found is due to Young. And it was observed that the following expression satisfies the classical N-Baxter equation, which is the first line of this slide. Obviously, if this equation is called classical N-Baxter equation and we speak about the solution of Young, we expect that there are also solutions of Baxter. And indeed, this expression involving trigonometric functions is a solution of the classical N-Baxter equation. And the longest, but maybe the nicest expression involving elliptic functions of Jacobi provide a solution of this equation as well. So here you see, well, some pattern which is going to be discussed in what follows. All right, so maybe let me prove something. So I was told when I was a student that any mathematical talk should contain a proof, but I do not want to bother you with a complicated proof, so let me prove something easy and but also fundamental. So I want to show that the following expression, Casimir element divided by z, is always a solution of the classical N-Baxter equation. So first of all, you might ask what is Casimir element. Maybe you've heard in the framework of Lie algebra, so I'm almost sure about that. But still, let me recall you that every finite dimensional Lie algebra admits distinguished form called killing. And simplicity implies that this form is non-degenerate. So for SLN, the killing form is just a rescaling of the trace form. But the key property of the killing form is its invariance. So for simple Lie algebras, killing form is well, non-degenerate and invariant. It has some implications. So firstly, as any bilinear form, it allows me to map double tensor product with vector space endomorphism my Lie algebra G. And non-degeneracy implies that this map F is an isomorphism. But the condition of invariance has another impact. Invariance says that this isomorphism F is an isomorphism of representations with respect to module structure. Now, in the space of endomorphism of G, there is a distinguished element, namely identity. And I can take inverse of that with respect to my map F. And this preimage of identity is precisely a Casimir element. So it is a unique element determined, well, by the structure, by simple Lie algebra itself. And, well, I'm sure you've heard this statement already many times in your life. Casimir element admits this commutativity property, which is actually another way to rephrase that it comes from identity and F is an isomorphism of G. But now it's actually everything what I need to show that the above expression is indeed a solution of the classical Baxter equation. Because just by formal manipulation, I can establish this to vanishing for gammas, and they imply that the classical unboxed identity for the above expression is fulfilled. So it's all one needs to prove that we have this distinguished solution of the classical unboxed equation. Okay, so we have seen at least one solution of this equation. Now, let me outline you some applications. So actually, what I'm going to tell you now is not a mainstream at all. So, but still, it's the easiest way to show you why this equation has anything to do with something analytic. So again, I take the data I started with, tensor valued meromorphic function of one variable. Now, let me fix some family of finite dimensional representations of G. And then I produce the following functions Rij for any pair of indices I not equal to J. So firstly, I apply my function R, and then for any pair I and J, I have this map, well, which explains in which factors I have an operation. So any Vi is a representation of G. And now I have such Rij. And an observation due to Ivan Cherednik is the following. So I can take a differential operator of first order. And the condition that this operator's commute is equivalent to the statement that the small r, the function which defines after all this operator, satisfies the classical Baxter equation. And this condition of commutativity is also a condition of flatness of some connection. So it's at least an illustration how solutions of the classical Baxter equation could arise in some application. But let me stress again, so it is not the main thing people do with the classical Baxter equation. So the main area of application is rather the theory of Lie Poisson groups, Boston Adler Syme scheme, in classical integrable systems, and also algebraic counterparts like Libby algebras and relating questions on quantum groups. All right, so now I would like to state for further properties another version of the classical indexed equation. So I stated it for the base field being the field of complex numbers, but the base field of real numbers matters as well. So especially in the light of possible applications to integrable systems. But the theory becomes more technical. So if we go from C to R. Still, in both cases, there is another way to state the classical indexed equation. And now my function has two parameters. So it is a function not of one variable, but of two. And I write the condition on R in a way which is longer, but maybe even more transparent. Yeah, so I take again a sum of three commutators. So the same thing with upper indices. But now at least you can follow the logic what I plug in. And it's again a condition on a tensor valued function R. And usually people require also the condition of skew symmetry of this. So it is a so-called classical indexed equation with two spectral parameters. And in this realization of this equation, it is more convenient to speak about possible transformations. Namely, for any, function phi with values in the automorphism property. So actually here, when I write comma, maybe I had to say, I speak about germs. So I say my meromorphic function is defined in some unspecified small neighborhood of the origin. So if phi is a parameter-dependent automorphism, actually it has to be analytic. Then I can transform my solution R and get another solution which is equivalent to the original one, well, by the definition. Next, so obviously, if I take any geomorphism eta, so actually, I'm not saying it is an isomorphism, by the way. For instance, taking the square of the variable. Well, obviously, if I had a solution, then I get a new solution. If my old solution was skew-symmetric, the new solution will be again a skew-symmetric. So these are two types of transformations I can do with the above equation. And important lemma established by Belavin and Renfeld is that over complex numbers, any solution of the classical unboxed equation 2 is equivalent to a solution which depends on the difference of variables. And if I write the condition for my function rho, well, then I recover the first version of the classical indexed equation. So there is classical indexed equation 1 and classical indexed equation 2 in my talk. All right, so we introduced the indexed equation. What natural question can arise now? So I said some words that it is important in applications, but people might ask why is it difficult to find solutions of this equation? And it is very easy to give an answer to this question. Namely, let me call the dimension of my Lie algebra G M. Well, then a tensor valued function R is given by M to the square parameters. I can choose, for instance, a basis in G, then in this basis of G tens of G, I have to specify M square coefficients of my R. So M square parameters, but we have conditions on the function R in the triple tensor problem. And it turns out that for these M square parameters, we have, well, approximately M power 3 constraints. Meaning that the classical Baxter equation is a largely overdetermined system of constraints on these coefficients of my function R. And a priori, there should be no solutions of this equation at all. But since we have seen already some solution and even a proof that solution of Young is a solution, it indicates that this equation is expected to have very interesting structures. Okay, so I told you that it is difficult to find solutions of this equation, and being overdeterminant also implies that it is hard to apply numerical methods to find such a solution. So now I'm going to say something completely opposite to what I've said before. Namely, I claim that it is very easy to produce some solutions of this equation. And here is one possible recipe. So let's A and B be a pair of commuting elements. Then one can check, and it is not hard at all, that this expression is a rational solution of the classical Baxter equation. So it is a solution, it satisfies the Bauer identity. And it has the following consequence. So whenever I have a pair of commuting elements, I have a solution. Now one can ask, so can we classify in the Lie algebra SLN all pairs of commuting elements, say up to automorphism of my Lie algebra? And the answer is actually no. So it is a very old observation of Gelfand and Ponomarev that you cannot describe normal forms of pairs of commuting square matrices. And it also shows that in SLNC, you cannot classify pairs of commuting elements. So there is a very special meaning to say that we cannot classify. Namely, there is a notion of representation wildness, which occurs in this case, which in particular says that solutions of this type cannot be actually classified. So on the one hand side, it's hard to find solutions. On the other hand, I told here there are solutions which are impossible to classify. So what is going on here? So actually, what is helpful at some moment is to have some geometric picture, which can explain what is going on here at all. Okay, maybe some moment I have to say, and I thought the right moment is now, is that also this equation is called an Baxter equation. Neither Young nor Baxter really studied. So on the left picture, you see Young. Young is American physicist of Chinese origin. A recipe of Nobel Prize in Physics, by the way. So Young-Mills theory is named by the same Young. And Rodney Baxter is a mathematical physicist from Australia. So in the 60s, they both studied certain solvable models of theoretical physics. And after that, it turned out that they are controlled by certain solutions of the quantum Baxter equation. But the actual introduction of the Baxter equation is a great achievement of Ludwig Faddeev and his group. I also have to add that the quantum Baxter equation appeared first, and then Sklanin and then independently Belavin introduced the classical and Beck's equation I'm talking about. So it is some little comment about the history. Now let me show you again, well, the list of solutions which appeared already in some previous slide of mine. And I want to draw your attention to the following facts. So in the solution of Young, we have seen also a way to generalize it. So we take Casimir element and divide by Z. Next, you can also observe that in the two remaining solutions, all coefficients have only simple poles. They have poles, but poles are simple. If I take the residue, is of the trigonometric solution or of the elliptic solution, we can convince ourselves that the residue is a Casimir element. And it is, in fact, always so up over scale. Moreover, if you look on the coefficients, there is even or odd functions. And it's, again, not a coincidence at all. And the structure theory of the classical and Beck's equation was clarified in a seminal work due to Belavin and Drinfeld. And now let me state the classification result. So here is the equation I am talking about. So it is a classical and Beck's equation 1. So dependence of one spectral parameter. So for any solution, we can say the following things. So such a solution is always symmetric, automatically. And we have seen it actually on the previous slides in examples. So when I said coefficients are either even or odd, so one can say it even stronger, saying that solution is automatically symmetric. Then any solution has a simple pole at 0. Now it has a residue which is a multiple of the Casimir element, and moreover, poles of this solution form a discrete subgroup. So poles can be trivial, but it could be a full lattice. And in this case, we speak about elliptic solutions. So it could be Z. The rank of the group lambda is 1. And lambda can be trivial. So in this case, we speak about rational solutions. So any solution of the classical indexed equation is either elliptic or trigonometric or rational. Remarkably enough, elliptic solutions exist only for the Lie algebra SLNC. So SLNC is the easiest case of simple Lie algebras, but surprisingly also the richest one. Well, we have this trichotomy result, elliptic, trigonometric, and rational, and on the pragmatic level, we have seen it on example, the previous slide. So coefficients are either rational functions or trigonometric functions or elliptic. Belavin and Drinfeld also classified all elliptic solutions. Previously, Belavin discovered all solutions, and together with Drinfeld, it was shown that this list is full. The classification of trigonometric solutions was done in that work as well, but it is a very complicated result, which involves very deep techniques from the theory of the algebras. Beautiful theory, but rather involved. And I told you that for rational solutions, we cannot classify all of them. In that case, the classification problem contains a representation via subgroup. So maybe you can ask why this trichotomy. So I will proceed to algebraic geometry, giving some answer to that. But there is another way to give an evidence to this statement. So if we write the classical indexed equation in this form, well, then we see that after all it boils down to some addition theorems. And there is a very old classical result of Meerberg saying that addition theorems exist only in genus 1. So only for elliptic curves or its degenerations. And actually this idea was used by Belavin and Drinfeld to prove this trichotomy result. But the appearance of elliptic trigonometric and rational, so it's not accidental at all. I have to say a couple of words about trigonometric solutions. So the first solution ever found was due to Kulish, a student of Padeborn who introduced the quantum indexed equation. And here's the formula. So the expression involves root system of the Lie algebra. So it's a nice, beautiful expression. So you see Casimir element and then an expression involving positive and negative roots. In general, so if you want to write formula for general trigonometric solutions, so the answer involves very essentially and deeply the theory of loop algebras and affine Lie algebras. So in this respect, I want to mention one lemma of Belavin and Drinfeld, which says that for any trigonometric solution, we have this nice property. So if we agree that the poles of rho are 2 pi I z, so poles form a group isomorphic to z, so if we rescale it to this way, then any solution leads to an automorphism sigma of my Lie algebra of finite order, satisfying this monodromy condition. And appearance of this sigma also explains a result which was also clarified in a joint work of mine with my student Rashid Abedin, that one can understand theory of trigonometric solutions speaking about Lie algebra structures on twisted loop algebras. So one can speak about loop algebras, they can be also twisted, it is related to affine Lie algebras. Lie algebras is algebra, so it will not be the topic of my talk, but I thought it would be nice to mention. Now let me show you how one can treat solutions of the classical indexed equation and how algebraic geometry actually arises in this. So for this, I take the Lie algebra of formal currents. So G double bracket Z means that I take Lie algebra of formal Laurent series in Z. It is, of course, a Lie algebra, and this algebra is equipped with a degenerate bilinear form. So here maybe I have to explain what is going on. So kappa is a Killing form. So F and G are elements of my Lie algebra R. Kappa of them is an element of bold K. So bold K. So unfortunately, I have not written what is bold K, but bold K is algebra formal Laurent power series in Z. So here, kappa of Fg is a formal Laurent series, and I can take its residue at 0. Summing up, F is a bilinear form. F is bilinear. F is invariant because Killing form is invariant, and is also non-degenerate. It also is not difficult to show. So the Lie algebra of currents has a distinguished invariant form. Well, now let me take an expression R Casimir divided by y minus x, well, plus some formal power series t. So t does not have any singularities. Well, now I think it's going to be a bit heavy, and maybe let's ignore the details. So you can play with coefficients of R. So you can produce a power series expansion in Y, play with that. And after all, the goal is to define a vector space V. So V is a vector space in R associated to any function R. And then an old observation due to Cherednik and Gelfand tells the following. So when we follow the recipe, we start with such a power series R and produce a vector space V. Then we have a direct sum decomposition. And R is a solution of the classical index equation if and only if V is a Lagrangian Lie-Sab algebra. So being Lie-Sab algebra, it is clear what I mean. So V is closed and the bracket in R. And being Lagrangian means that V is equal to its orthogonal with respect to the form F on the second line of the slide. Moreover, yes, so this datum, Lie algebra R with a form in such a direct sum decomposition into a direct sum of two Lie-Sab algebras, was called later on Manin. And such decompositions of a Lie algebra into a direct sum of two Lie-Sab algebras appeared in the late 70s in the Adler-Constantin scheme. So this observation due to Cherednik and Gelfand was, of course, inspired by that development. And the story is the following, after all. So let me take a function R, and structure results of Belavan and Drinfeld tell us that any solution of Jan-Baxter equation after transformations can take this form. So Casimir element divided by something plus something regular in the neighborhood of the origin. So if we want to study solutions of Jan-Baxter equation, so this ansatz is general one. Then we associate to R a Lie-Sab algebra V. And we get a Manin tree. And actually, the statement was that we can go back. So if we have a Manin triple, then we can recover a tensor R. And to do it, so let me better show you examples. Instead of being formal, I think one example tells more, well, is it some involved formula. So let us start with the easiest Manin triple we can ever imagine. So we speak about Laurent power series. Of course, it is a direct sum of formal power series without singularities, and we have a singular tail, which is the second cement. So both cements are Lie-Sab algebras, obviously. And it is also trivial that these subalgebras are isotropic with respect to the form I introduced. So it follows very easily from the formula I gave. And actually, isotropy implies a property to be Lagrangian by some very easy linear algebra. Now, I do the following thing. So I take an orthonormal basis of G, and here I have to apologize. So this bold K is either R or C. So I want to stress that my base field could be also the field of real numbers. So it is not this power series ring. So I tried to introduce before. So it is ours. And kappa is a killing form. It is non-degenerate. I can find a non-normal basis. Then having a basis of G, I can produce a basis of the Lie algebra V, which is in this case Z minus 1, G, Z minus 1. So it is clear that elements J, K form such a basis if I allow K to be any negative integer. So it's a true basis of V, and we can speak about the dual basis in the topological sense because, well, we have, well, of course, some issues here, but we can speak about the dual basis for the Lie algebra formal power series. And now we can produce the following expression associated with my Lie algebra V. So I take a sum over all basis element of V times the dual basis. And now let me write explicitly what I have in mind. So I just applied here the definition, but you observe here that I take y at the first argument and x at the second argument by purpose. Now I have such an expression, and this double sum is actually a product of two usual sums. So it's very special for this setting. But now, after this transformation, we see that the second factor is just a Casimir element. It's a way to say what is a Casimir element for simple Lie algebra concretely. And the first factor can be computed because we just speak about the geometric series. So here is the answer. And simplifying, we simply get the solution of Young. So the solution of Young corresponds to the Lie algebra W, the easiest one we can imagine. And this pattern to go from Lie algebra to a solution of Young-Baxter equation is a very general one. So we can do it in general, which is some basis, dual basis. A difficult thing is, of course, to make sense of this infinite sum. And please don't bother about any convergence issues. So, of course, they exist here, but one can circumvent them. And it is how the Cherednik-Gelfand correspondence works. Now I would like to draw your attention to the following fact. So if I have a Lie algebra W in R, then I can speak about the so-called algebra of multiplicators. So these are those formal power Laurent series which stabilize my Lie algebra. And in this case, since W is Z minus 1, polynomials in Z minus 1, it's trivial to conclude that we speak about polynomials, the variable Z minus 1. Which tells us actually nothing. So actually, it can even be a bit misleading. And follow us to wrong conclusions. And because of that, let me speak about Manin triples for constant rational solutions. So constant rational solutions have the following shape: Young's solution for some perturbation given by a constant tensor. And I mentioned that there are many such tensors, for instance, A tensor B minus B tensor A for A and B. I mentioned it when I told you that the problem of classification of such solution is representation well. Okay, so it is what we can take. Now, if we compute the corresponding Lisa algebra W, well, of course, it depends on this perturbation tensor T, but qualitatively, we take all the polynomials in sufficiently low degree, but also there is some term really depending on it. And now the thing is following. So if we consider the algebra of multiplicators of solutions of this form, well, then it is easy to see that any such W is stabilized by multiplication with Z minus 1. So it is also stabilized by multiplications by Z minus 3, also by any further negative powers of Z, but not necessarily by Z minus 1. But important thing is that this algebra has another obvious realization. And now we see here the equation defining a cuspidal cube. And it is the reason why algebraic geometry enters into the theory of the classical indexed equation. So it will be explained on the next slide, but here is the way. So we have a Lisa algebra W, and we shall speak about this algebra of multiplicators, which will be our path to algebraic geometry. Yeah, so I told you I want to study neuromorphic solutions of the classical indexed equations, Q-symmetric. The theorem of Gelfand and Cherednik tells us that we have to study such Lagrangian decompositions. But now, well, results which were not proven immediately. So actually it took quite a while to fix what is going on here at all. And the way I present the algebra geometric theory of the classical indexed equation actually does not reflect the historical development of the subject. But I think finally summarizing, it's maybe the best way to proceed. And the first statement is that for any such Lie subalgebra W corresponding to a solution of the classical indexed equation, the algebra of multiplicators is non-trivial, and it contains the coordinate ring of some plane. And actually, it is equal to the coordinate ring of a plane cubic in all the cases but this case of the solution of Young. The solution of Young, the simplest one, could have led us to a very wrong conclusion, but the story is actually like this. So we go towards plane curves of genus 0. It is not difficult to show that W is actually a finitely generated torsion-free module. Now, if we have, well, of interest is, of course, this affine plane cubic. We have a finitely generated module, which is also a Lie algebra over R. We can go from a fine picture to projective one. So to compactify a plane cubic, we need only one point in infinity. It's a very basic algebraic geometry. And another thing is that this pair W and this algebra allows us to construct a sheaf of Lie algebras on a projective curve in a unique way. If we say, well, on a affine path it's W, the sheaf should have vanishing cohomology. And there is also a condition, it's a behavior at this point which compactifies my plane cubic. So namely, well, it's a bit technical, maybe it's better even to ignore it for first reading, but still let me say, so on a plane cubic, we have a unique regular differential form. It is unique up to scalar because space of sections of regular differential forms is one-dimensional. So this omega is unique up to rescaling. And since it is unique, so we can fix it. And there is a unique choice of coordinates identifying this form at O with dz. Well, and there is some requirement of this way. So anyway, so it's a valid theorem. And actually, well, this pattern appears at several other places where there is an interplay of algebraic geometry and mathematical physics, for instance, in Krzywa correspondence. And this year, when we speak about commuting differential operators and geometric data. All right, so it is a theorem, and here you see the first appearance of algebra geometric data, namely some plane curve of genus 1, irreducible, and a sheaf of Lie algebras. So the basic geometry tells, of course, that a plane cubic can be of three types. And the type is fixed by the discriminant of the family. So generically, we speak about elliptic curves. And if discriminant is 0, then curve is singular. So it is nodal, and it could be cuspidal when both parameters G2 and G3 are 0. So there are three types of Weierstrass cubics and three types of solutions. The next result will be that the type of the curve actually fixes the type of the solution. Yeah. And elliptic corresponds to elliptic, nodal corresponds to trigonometric, and cuspidal corresponds to rational. So if you prefer Riemann surfaces, then well, here is a corresponding complex analytic. So in mathematical physics, sometimes people like to speak about torus, cylinder, and the sphere, and it's just the same thing. So now let me go towards the results. So let us sum up what we have. So we work with irreducible cubic curve. So it has a distinguished point at infinity. So A is a sheaf of Lie algebras with vanishing cohomologies, in particular, no global sections, which in particular implies that A has no torsion. It is a sheaf of Lie algebras, and its phi bar is G for an arbitrary smooth point, but not necessarily for the singular point. So at the singular point, there is a condition which I will explain you later, but the geometric theory underlying the classical Yang-Baxter equation is the following. So if I have a solution of Yang-Baxter equation, I can produce a geometric datum, curve and a sheaf of Lie algebras with properties as above. And actually, conversely, the same is true. So pairs of E and A up to a natural equivalence corresponds to equivalence classes of solutions. So it is the way how one can give a classification of solutions of the classical Yang-Baxter equation. And when I speak about algebraic geometric theory of it, this is what I have in mind. So moreover, in this pair, being elliptic for solution means the curve is smooth, trigonometric means nodal. And here, actually, I can even tell you what are sections of my sheaf on the smooth part of my curve. So each check is a smooth part. So I necessarily have the algebra of twisted loops. So maybe just the Lie algebra of Laurent polynomials if sigma is trivial, but in general, we have here an isomorphism of finite order over C. So where else it's a current project of mine to see what it's going to call over R. So the theory turns out to be richer over reals. But over rationals, so solution is rational is if and only if curve is cuspidal. And here it is even easier to say what are possible sections over the regular parts. These are just polynomials with coefficients in G. So the statement is solution determines a geometric datum, but geometric datum gives us back a solution. And now I want to tell you how do I do it. Yeah, so I told you so far that there is a way to start with a solution and produce an algebra geometric datum, but one can go back as well. And actually, so having algebra geometric background, it's not difficult to see what is going on, because I think that most of you are aware of MaPhyAG sequences, and for curves, so there is an exact sequence of these forms. I take any point of my curve, smooth or singular, and I get such a sequence involving global sections and the first cohomology. And here I have sections over the complement of pi, completion of the germ of pi, and the rational hull of my germ. So it is an exact sequence of my and Vietoris. But I told you that my sheaf A has no cohomology. So since we have no cohomology, well, first term vanishes, last term vanishes, and I have such a direct sum decomposition. And actually, it is a Manin triple. So I have one Lie algebra, another Lie algebra, and so on. So for a distinguished point at infinity, I get Manin triple from the theorem of Gelfand and Cherednik. So the logic was that if I have such a Manin triple, I can produce an algebra geometric datum. And my Vietoris sequence allows me to come back. So it is how we can think about one-to-one correspondence. However, we have here freedom to choose a point pi. And of course, as frequently in geometry, interesting things happen at singularities. And if my curve is cuspidal and I take a singular point, I can do it. And sections of the complement of pi are g of z, whereas I cannot say what is my second summand. So, but still I get a Manin triple of this shape. And I can rephrase it differently. So I can say, let us start with W having this property, it gives me some solution. This solution will be rational, and it is precisely how the theory of Alexander Stolin, rational solutions, works. So his result says, if you want to study rational solutions, describe such possible Ws. So it happens for the cuspidal curve. For nodal curve, if we get a singular point, then we get again a Manin triple, so completions of loop algebras. If we have no twist, so we have a Manin triple of this form, Laurent power series in G. It can be embedded in two ways into series. Z plus and Z minus corresponds to say that Z is Z plus or Z is Z minus minus 1. And there is a complement. And here, the conclusion is that if we want to describe trigonometric solutions, then we have to describe such possible Ws also in a twisted set. And this observation is due to Abedin and myself, and it was a new contribution to the theory of the classical index equation. So it is maybe the first result when algebraic geometry told something new to a very well-established theory of the classical index equation. So once again, so to describe trigonometric solutions, I have to describe W's, giving such a direct sum decomposition. And this is why we get the geometrization of trigonometric solution. So I also want to go very quickly about a different pattern to associate a solution of Yang-Baxter equation to geometric data. So anytime I start with Weierstrass cube, and the important property of it is that it has a unique up to scalar regular differential form. So the dualizing sheaf is trivial, and in particular for elliptic curves and degenerations, we have a very special form of the cell value, just due to the fact that the dualizing sheaf is trivial. Now, well, I'm afraid I have to be very quick, and it could be a bit fast. So, but still, I want to mention that there is another way to associate a solution of the classical Yang-Baxter equation to a geometric datum. So again, so my geometric datum is a curve of genus 1, sheaf of Lie algebras with vanishing cohomology. Its fibers over smooth points are G, but over the singular point, well, the condition is a bit more tricky. But these conditions imply that sheaf is torsion-free, and over the regular path, Killing form allows to use such an identification. Now, there is a condition at the singular point. So maybe let me again run quickly through the slide. So I take a geometric datum. A is a sheaf of Lie algebras, and it admits the so-called rational hull. So it is a Lie algebra over the field of rational functions of my curve. So again, simple. And this Gothic A admits a distinguishable linear form. When I compose Killing form with taking residues with respect to this distinguished differential form at the singular point with residue taken in the Rosen sense. So there is something to be said, but the condition at the singular point is the isotropic condition for the germ of my sheaf A at this point. So if I have a singular point, but let me tell you that this condition is automatically satisfied if the fiber at the singular point is G. So then we do not have to bother at all. So now, well, unfortunately, I have to be very quick, but I hope still that people with algebra geometric background can follow. So I start with a geometric datum, and I embed the regular path, well, diagonally into the product, my curve with a regular path. So I have a distinguished differential form. So firstly, we have a distinguished sequence called residue sequence. And here, nothing deep happens, so I take in the middle a meromorphic function, possibly with a pole, and take its residue. But it can be formulated sheaf theoretically. So there is an explicit way to do it. Now, in my geometric datum, I have a curve and a sheaf of Lie algebras. And I can pull back my sheaf A and its restriction on the regular path on my curve multiplied with its regular path. So I have this sheaf A box times A check. It's some sheaf, and I can tensor my sequence, my residue sequence with this sheaf. And because diagonal is flat, my sequence will remain exact. And now I apply homology sequence to this and use the fact that I have Q-not formula. And I use the fact that my sheaf A has vanishing cohomology. So if I apply global sections, then, well, there is some cohomology vanishing, which implies that I have some very nice isomorphism of vector spaces. And now there is a following diagram. So maybe it's hard to follow, but still let me try to explain what this is. So we maybe start here in the morphism of HF. And here there is a distinguished element identity. I have a canonical map TV, and there is also the residue isomorphism, which is induced by the residue map. So all maps here are isomorphism about this inclusion. But at the end of the day, what I want to have, so I have something here, and I produce a distinguished section. And this diagram shows that we actually can produce a section going a different path. So I have a distinguished section which is determined solely by my geometric data curve and shift with vanishing cohomology. And it was observed first by Cherednik in a very short note in 1983, and then was generalized and put in a broader context by Gallinat by myself, that this distinguished section satisfies shift theoretic version of the classical index. And it's another way to say what has to be done to start with a geometric datum and produce a solution of the classical index. Namely, so we start a datum. So I remind you again what I impose. A is the sheaf of Lie algebras, coherent, no cohomologous, our smooth points, fibers are G. There is a condition which is technical at singular point. Then there is a distinguished section. And if we trivialize this section in the neighborhood of the point at infinity, then we get a non-solution of the classical indexed equation with two parameters, well, depending on the trivialization, and another choice of trivialization leads to HP1. So either we take my Viatorius sequences or we produce this distinguished section. So it's a way to associate a solution to a geometric datum. And it turns out that computing the section raw can be made more constructive. So maybe the remaining 2 slides are dedicated to the case. So how can we find such a sheaf A in a natural way? Yeah, what is for us primary, geometry or solutions of index equation? And there is the following way to construct such a sheaf A of Lie algebras for the Lie algebra SLN. And to tell you what is going on, I want to remind you that on an elliptic curve, an incomposable vector bundle is determined by its rank, degree, and a continuous moduli. It's a very old result of ITEA. So in representation theory, we speak about representation time situation. Now we can impose even more, not just in the composability, but simplicity. So we say we fix topological invariance and want our vector bundle to be similar. Well, then it happens if and only if rank and degree are coprime. And ITEA's theorem tells that this set is non-empty if and only if rank and degree are coprime. And simple vector bundles are determined by their determinants. Well, then one can also prove that Jacobian acts transitively on this moduli space. And about 20 years ago, me and then But you can just prove the same package for Weierstrass cubics. So actually, it was not as surprising at the time. There were also alternative approaches. But we also developed a technique how to work with vector bundles in a constructive way. It was also needed in the applications. So now, in the same way, we construct the Lie algebra SLV associated to a vector space V, we can construct a sheaf of Lie algebras associated with a vector one. So I think most of people in the audience have seen this at P. So I have trace map from shift endomorphism of pi to O. And this at pi is actually a sheaf of Lie algebras, fibers are SLNs. Because of the transitivity of the action of the Jacobian, the sheaf does not depend on the continuous moduli. It is determined by the span in D only. And one can also rescale to achieve that D is smaller than n, D is mutually prime to n. And this sheaf has vanishing cohomology because of the long exact sequence. So the condition of simplicity implies this vanishing cohomology. And summing up, so if I have a Weierstrass cubic, a pair of coprime integers, then there is a distinguished family of solutions of in-Baxter equation. One can compute it, and it was done in my works. And maybe let me conclude my talk with an example of what is going on for rank 2 and degree 1. So for elliptic curves, we get a solution of Baxter. For nodal curve, we get another trigonometric solution discovered by Cherednik. And for cuspidal curves, there is one more solution discovered by Stolin. So for SL2, one can actually give a full list of solutions. They all carry some names. And it is not surprising that we recover something well known. But going to higher end, we also got some solutions with expressions in doubt. Well, so thank you for your attention. And, well, you are welcome to pose questions if there are any.
Well, thank you, Igor, for your talk. Is there any question in the audience? Let me check the YouTube channel. No, there is no. Well, I have a couple of questions. I shall be fast because we are already a little bit over the time. Well, for the last, I mean, you say rank 2, and I mean, for the last part when you are using the more algebraic geometric approach with vector vectors and so on, you say you explicitly wrote G equal to SLN. Is only developed for SLN or is for more Lie algebras?
Well, so the reason why we have SLN is SLN corresponds to vector bundles on curves. So if we want not SLN but something else, apparently we have to work with principal bundles. I have not worked with that.
Okay,
so,
yeah, to deal with vector bundles instead of, and also, well, this is a question from the beginning. I mean, the equations are for G as simple Lie algebra. How does it glue for constructing equations for other Lie algebras? I mean, because I mean, you have the bricks of construction of Lie algebras. No, can you construct equations for reductive Lie algebras out of these equations or something like that? I don't
so
know.
you say that we can replace simple Lie algebras by something more general?
Yes.
Well, there is, so for some structure results of Belavan and Drinfeld, it's important to have a simple Lie algebra. So even being semi-simple is not sufficient, strangely.
Okay.
But on the other hand, so I can very well imagine that, well, a lot of what I told you here can be done for arbitrarily the algebras without any constraints. It will not be one-to-one, yeah, but
Also,
so,
I mean, this is from the generalization on the Lie algebra part, but also you have talked about the, I mean, all the possible planar curves. I mean, you have elliptic, nodal, and cuspidal curves, and you
yeah.
have a classification theory for solutions of Young-Buster equations. Do you know anything, I mean, in general, for the whole space of solutions of Jack-Buster equations? Because it seems that you can, even from the geometrical point of view, write a family of solutions over the moduli space of elliptic curves and I mean, and with
Ah,
no curves, I mean, the closed moduli space, and then, um,
so
you
you
know,
want you,
have
you
a
want
moduli
to
space of
say
curves.
can we do it in families?
Yes.
It's very actually very interesting. So and maybe if I am allowed, so since you asked a question I really like, so let me share my slide with you once again. So sorry about that. But indeed, you can write in a family. Yeah, you can do
Mhm.
it, and we did it. In particular, together with Kreuzler, so, in some volume of the memoirs of the IMS. But look, what is then a conclusion? So I claim on the one hand side that these solutions come from the family. But on the other hand, so here you have elliptic curve. Here you have the generation. You have f tensor f. So where is f? Well, here there is f tensor f. But here there is, for instance, f tensor h. So where is f tensor h here? And the answer is you can write a family. You can do it. But when I give you such expressions, I told you that I have to make several choices. On each individual curve, I have to choose coordinates. I have to trivialize my vector bundle in an appropriate way.
Okay.
And if I do it, I get these nice expressions. But it is also possible to write a family, well, unifying calls a solution, which is very hard to do concretely. But a non-trivial conclusion of the algebra geometric series, for instance, that this solution of Stalin is the limit of the elliptic solution. And after it was discovered, so some authors wrote, well, gauge transformation, coordinate change, concrete limit to see it concretely. But it was not known before. Yeah,
I
but
see.
coming back to your question, if you want to work in family, you can do it. Maybe you even have to do it. So in the algebra geometric spirit. So it is possible to do.
Okay. But maybe you need to have a frame of your vector, I mean, on your vector bundle of families or constructed out of the
Yeah.
family, you will need some frame
Yeah.
to put this specific construction, I mean, specific conditions. Yeah.
It's very hard to implement concretely to end up with formula.
Yeah. Yeah, I see. Well, anyone, Enrique, Carlos, anyone wants to ask any question?
Yes, me. Igor, I guess you can do Fourier-Bucay transform for your solutions of the Young-Buster equations for the Weierstrass family or any appropriate integral function.
Well, I mean, why should I do Fourier-Bucay transform?
Well, because it's there and it allows you to go from one Weierstrass vibration to another one to the dual one, and then you can relate solutions.
Well, maybe so. Let me reinterpret your question. So you want some derived categories in this theory, right?
Well, in the large, yes, the right
Well,
category.
I am not sure, so I can really apply here Fourier-Bucay transforms. So at least I have not seen it. So of course, so
So you mean it's not direct to see that if you have one solution to the Jam-Buster equation and you apply it to your data, to your vector bundle, the Fourier-Mukai transform, then you are going to get another one. This is the point.
I have not done it yet, so I'm not sure what it concretely means, to be honest. So if you have a concrete idea, so it would be interesting, well, but maybe still, if I'm allowed to comment, so I told about my contribution to the theory of the classical and Baxter equation. So there is also an approach of Alexander Polishchuk, mainly to the so-called associative Yang-Baxter equation, which is a different story, but which is related to the classical Yang-Baxter equation. And the theory of the associative Yang-Baxter equation is very close to the homological mirror symmetry for elliptic curves, the generations. There are also Fukaya categories here, and definitely also derived categories. So, and well, one can do it, but it's a bit different thing. They are related but different. But of course, one can think about what are neighboring questions where it could go in very different directions.
Okay. Thank you.
I have a last question that I have it written down, but I forgot to ask you. Can you do this Drinfeld trick of reducing variables? That you have two variables and then can be expressed as a difference of variables. I mean, the solution can be expressed as a difference of these variables. Can you do it recursively? I mean,
well, I mean, you mean algorithmically?
I mean, having four variables and then
No, but there are only two. There are no four variables. So
okay.
There are two versions of the classical and Baxter equation, and you can say after transformations you can achieve this dependence of on difference. Yeah, so in principle, I think it's even constructive. So at some point, you have to solve a system of ordinary differential equations, which would be tricky.
Yeah. Yeah, let's go to analysis. Okay. Enrique, is there any other question?
No, just to thank Igor for his nice talk.
Well, thank you for coming.
Thank you, everyone. Thank you, Igor, for your amazing big talk, telling all of these results from several years. That was an impressive summary. So thank you very much.
Okay, thank you for the invitation. Hope to see you not via Zoom, but in presence at some moment in Madrid, somewhere
Yeah, you
else.
should come to Madrid, and also Leslie.
Okay, so
That will
thank
be
you very
wonderful.
much.
Thank you.
See you.
See you.
Stop.